Chapter 3, The Chemistry of Climate Change, Part 2. In this lecture, we'll be talking about the shapes of molecules and how those shapes influence whether or not they're greenhouse gases. We'll also talk briefly about the carbon cycle. First, let's review how to draw Lewis structures, as they'll be important in determining the shape of a molecule. First, count the total number of valence electrons. 2, place one bond to connect each atom to the central atom. 3, distribute the extra electrons on the outside atoms in pairs to fulfill the octet rule. 4, place extra electrons on the central atom. And 5, redistribute electrons by making double or triple bonds to fulfill the octet rule. Let's look at nitrogen as an example, N2. So first, let's count the number of valence electrons. It's in group 5. So it's 5 plus 5 for a total of 10 valence electrons. So now we draw a single bond to connect the two atoms. And we can start putting the remaining 8. We've put 2 electrons in the bond and used them up. We can put the remaining 8 on the atoms. There's no central atoms, so we're just doing the outer atoms until we get an octet on each. But wait a minute. We've used 2, 4, 6, 8, 10. We've used all 10 electrons. So now we're in trouble because this nitrogen does not have an octet. So what do? We redistribute the electrons like so. We need to put these and make them shared as well, because shared electrons will contribute to the octet of both atoms. So now this nitrogen has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. The shared electrons are seen as electrons for each atom in determining the octet. Now, there are different types of ways to visualize and express what a molecule looks like. There's the molecular formula, and then there are structural formulas, and we talked a little bit about these already. They're the Lewis structures, which actually show the connectivity. We could draw 3D structures using these wedges to indicate that the hydrogen is actually coming out of the plane of the screen towards us, and the other hydrogen is going into the plane of the screen. And then we've seen the shape or the space filling visual previously. So there's a film on molecular shapes that isn't very long. There's an additional optional video that is longer and goes into a nice but lengthier explanation for shapes. So if you felt that the first video you see now goes a little too quickly, you can go into Chapter 3, Part 2 under Optional Videos and take a look at that. So in the video, you saw them discuss the VSEPR model, or the valence shell electron pair repulsion. That's just a fancy way of saying electrons repel each other because they're negatively charged. So if you have one pair of electrons on an atom using the Lewis dot structure model, it's going to repel another pair of electrons. Therefore, they're going to be as far away from each other as possible. But remember, we need to try and visualize this in 3 dimensions. In 3 dimensions, for something like methane here, remaining in a flat plane where all the electron pairs in the bonds are at 90 degrees is not as far apart as they could be. In 3 dimensions, those lone pairs can be farther apart because, and I'm using this to show the hydrogen going into the plane of the screen, those dashed line, and then the wedge coming out of the screen. In 3 dimensions, those hydrogens can take on a tetrahedral shape. It looks something like a pyramid. And then the angle can be expanded so the distance between the electron pairs are optimized. That distance is even larger. So if all the electron pairs are bonded, you have a tetrahedral shape. If in the case of something like nitrogen, the Lewis structure looks something like this, okay, you have 3 bonding pairs, and then you also have a lone pair. So we call that a non-bonding pair or a lone pair. When you have a molecule with this 3-to-1 property, 3 bonding, 1 non-bonding, it takes on a trigonal pyramidal structure, sometimes called triangular pyramid. So in this last type of shape, we have 2 bonding and 2 non-bonding. So in this last shape, we have, again, 4 electron pairs. This time 2 are bonding and 2 non-bonding. So water is a good example. It forms 2 bonds to hydrogen, and I'm not really emphasizing the shape here, just that the oxygen has 2 lone pairs, and then 2 of the electron pairs are on the bonds, or in the bonds for the hydrogen atom. Whenever it's referring to these electron pairs, the number of bonding and non-bonding, it always is in the frame of reference for the central atom. So when you're looking at CH4, you're not thinking about the hydrogen atoms, or CF4, you're not thinking about the fluorine. You're focused on how many bonds are there to the central carbon, how many lone pairs or non-bonding pairs are on the central atom. Just like here in phosphorus trichloride, how many bonding pairs are on phosphorus, how many non-bonding pairs. So thinker buddy, by drawing the correct Lewis structure of carbon dioxide, determine which description of its molecular geometry and predicted bond angle would be correct. Linear is the correct answer. You should have seen that as one of the possible shapes in the video. So now let's go through it. You would have 4 electrons from the carbon because it's in group 4, and 6 from each oxygen for a total of 16 valence electrons to work with. Okay, so now we start with carbon as the central atom. The central atom will always be or generally will be the atom that's furthest to the left in the periodic table. We'll draw a single bond to each oxygen and start working on octets for oxygen. Okay, now we've used up all our 16 electrons. 2, 4, 6, 8. Same thing over here. So we need to make some double bonds. So the final structure, and this should be review of CO2, and it doesn't matter which lone pair you take to make your double bond, as long as it's one of them that's now shared by carbon. Carbon now has its octet because it's using these electrons here in its octet, and these oxygen atoms also have their octet. They're using the 4 from the double bond and the 2 from the each lone pair. So now how does molecular shape influence whether or not you have a greenhouse gas? Well, as we know already, there's quite a wide spectrum of light that comes from the sun. There's UV radiation, visible light, as well as infrared light. The Earth is warmed by this electromagnetic radiation, and then it re-emits some of them. when it re-emits, it emits in the IR frequency. Greenhouse gases then absorb certain IR frequencies. When they absorb those frequencies of infrared radiation, they're keeping it in our atmosphere. And that heat and that electromagnetic radiation does not escape. But how do we tell whether or not a gas absorbs infrared radiation or not? Now, when you start talking about longer wavelength of light, it won't break apart molecules, but instead cause them to vibrate. So the molecules absorb that energy, start twisting and stretching and vibrating, and then re-emitting that energy. But it doesn't actually break those molecules apart. So in this little animation, you see light is hitting this carbon dioxide molecule. It's wiggling around and then re-emitting the radiation back to the Earth. Now we can identify if a molecule absorbs infrared radiation by looking at what is called an IR spectrum. Basically, what we have is an instrument that shoots infrared light at a sample, in this case carbon dioxide, and it determines how much and what frequencies of light or wavelengths actually made it through the sample. So what was absorbed and what wasn't. If you have a greenhouse gas, then some of that infrared light would have been absorbed. And that's what we see here. This is percent transmittance. Okay? If carbon dioxide was not a greenhouse gas, we would have a spectrum that looked something like this. All of the infrared radiation would pass through. But what we see instead is that there are certain wavelengths of that infrared radiation that are being absorbed by the molecule. And strangely enough, for certain wavelengths, it has a very specific type of vibration for the molecule. So when you have this wavelength over here, between 10 and 20, and this is micrometers, it causes a type of scissoring effect for the carbon dioxide molecule. These two oxygen atoms go up and start to come closer together, and the carbon goes down. But at this wavelength, the molecule absorbs specifically this wavelength of IR radiation. It starts to go back and forth between these two atoms, and the other atom shoots out that way. These strange vibrations for very specific wavelengths. So again, if all the IR radiation passed through, we would see none of these dips. These dips show the IR radiation didn't go through, it was absorbed. And again, once these absorb that light, they can re-emit it back to the Earth. So instead of it escaping into the atmosphere, it is basically absorbed and then shot back to the Earth. And of course, if you remember, a certain amount of this is natural, and we need it in order to maintain a comfortable temperature on Earth. The problem arises when we don't have balance between the amount of greenhouse gases we need and the amount of greenhouse gases we're actually producing. This type of stretching requires higher energy than this type of bending. In order to stretch a molecule, you have to have infrared radiation that is shorter in wavelength. Bending takes less energy. Now, can we predict whether or not a molecule will absorb IR radiation without putting it in an instrument to obtain an IR absorption spectrum? We can, just by picturing how a molecule will stretch or bend and paying close attention to the distribution of electrons. If a stretch or bend causes an uneven distribution of electrons, then that molecule will be IR active. You'll have to know the shape as well as the atoms in the molecule to make this determination. Let's look at O2. It doesn't matter how O2 stretches and it has limited bending. The electrons are distributed evenly. So there's our O2. Now if we stretch them apart, these oxygen atoms still have equal pull on the electrons since they're identical atoms. There's no uneven distribution of electrons around these molecules from here to here. And this is actually true of every molecule that has two identical atoms. It will not absorb IR radiation. Now let's look at a diatomic molecule with two different atoms. For example, oxygen and nitrogen. If you think about it bending and stretching, will that influence the distribution of electrons? So here we have oxygen and nitrogen. Oxygen has a bit greater pull on the electrons than nitrogen. These are different atoms. So now when we pull them apart, do we still have the same distribution of electrons? Well, the answer is no. If these atoms have different properties and different pull on the electrons, when you start moving the oxygen away from the nitrogen, it's going to grab more of the electron cloud and bring it towards itself. So, in fact, in any diatomic molecule with two different atoms will absorb IR radiation, such as carbon monoxide. So, a minimum of two atoms are needed for stretching bonds, and those two atoms must be different in order for it to shift the density or distribution of electrons. This is also referred to as a dipole moment, that when that electron density is uneven, a dipole moment forms. Just like the poles of a magnet, you start to have one region of more electron density and another region of less electron density. You have to have three atoms in order for a molecule to bend. And this means our greenhouse gases include carbon dioxide, water, CFCs, ozone, nitrous oxide, NOx, all the NOx molecules, and methane. Some molecules that are not greenhouse gases would be nitrogen, oxygen, argon. Please explore the carbon cycle in the next video. Thinker Buddy. The carbon cycle describes the exchange of carbon between the atmosphere, land, and water. Which processes add carbon in the form of carbon dioxide to the atmosphere? Roman numeral 1, deforestation by cutting and burning trees. Roman numeral 2, deposition of calcium carbonate in the oceans. Roman numeral 3, combustion of fossil fuels. Roman numeral 4, respiration of humans and animals. Which one of those Roman numerals can be more than one? Add carbon dioxide to the atmosphere. All of them do except for the deposition of calcium carbonate in the oceans. That ends Chapter 3, Part 2.